Look at our planet from space, and the story seems simple. Earth is a blue marble, completely dominated by water, over a dry, rocky crust. But that solid rock beneath the ocean floor hides a massive blind spot. We know very little about what happens deep inside our own planet, because we simply can't dig far enough down to see it. The absolute limit of human excavation is sitting under a rusted metal cap in Russia. This is the Kola Super Deep Borehole, and it reaches exactly 12,226 meters into the crust. 12 kilometers sounds deep, until you look at the actual scale of the planet. Earth's radius is nearly 6,400 kilometers. Our deepest hole barely scratches a fraction of a percent of the way to the center. Everything past that microscopic pinprick is a world we have never directly seen. And in that dark, inaccessible space, geologists have found evidence of something completely unexpected. Between 400 and 660 kilometers beneath your feet, there appears to be a massive reservoir of water. Based on seismic readings and deep earth mineral samples, researchers calculate this reservoir could hold as much water as every surface ocean combined, or more. But if you traveled down there, you wouldn't need a submarine, no subterranean caves, and you couldn't swim in it, because this water isn't liquid. To understand how an entire ocean hides in solid rock, we have to look closely at what extreme physical pressure does to the building blocks of the planet. As you descend past the crust and into the Earth's mantle, the temperature and pressure scale up exponentially. Eventually, you hit a layer called the transition zone. Down here, the physical forces are so intense that the normal structural rules of geology start to warp. Under these exact conditions, common minerals are forced to reorganize their atoms, forging an entirely different material called ringwoodite. Since we can't drill down into the transition zone to collect it, we have to wait for the planet to bring it up to us. Deep Earth diamonds form in this exact layer. As eruptions push them to the surface, they occasionally trap microscopic fragments of surrounding rock inside them. When scientists examined these tiny sealed inclusions, they found pure ringwoodite. And more importantly, they found that the ringwoodite was packed with the chemical components of water. To see how that works, we have to zoom out of the macrogeography and look directly into the atomic structure of the crystal itself. Mantle pressure squeezes hydrogen and oxygen directly into the empty gaps of the mineral's lattice. The rock behaves like a sponge, finding the raw ingredients of water chemically. Multiply that capacity across the transition zone, creating a reservoir large enough to hold an ocean. At these extreme depths, the term ocean describes a chemical state of the rock itself, a mineral blanket wrapping around the interior of the planet with a massive volumetric capacity. When you take that microscopic mechanism and apply it to the entire Earth, you realize our planet is running a massive hidden engine. The familiar cycle of rain, rivers, and evaporation occurs entirely on the surface, but this loop actually extends hundreds of kilometers down, crossing the boundary into the deep mantle. At the bottom of the ocean, tectonic plates are constantly colliding. One plate is forced underneath another in a process called subduction, and as that crust is dragged down into the mantle, it pulls massive amounts of surface water and hydrated minerals right along with it. Once that trapped water reaches the extreme heat of the mantle, it acts as a catalyst. It lowers the melting point of the surrounding rock, generating huge plumes of buoyant magma that begin forcing their way back up through the crust. Eventually, that pressure finds an exit. Over millions of years, active volcanoes continuously vent that deeply trapped water back into the atmosphere as steam. Earth is operating a gigantic closed-loop recycling system, slowly trading oceans of water between the sky and the deep interior over geological timescales. Which brings us to the ultimate question about this water. Where did the oceans covering our surface actually come from in the first place? For decades, a dominant theory was that our water arrived via thousands of icy asteroid impacts during the early days of the solar system. But the existence of hydrated ringwoodite offers a different explanation. The surface oceans might actually be the result of the planet sweating. Billions of years of volcanic activity slowly baking water out of the mantle, pushing it up from the deep interior until it pooled across the crust. The water we sail on and the rain that sustains us are the visible products of this massive internal engine. This invisible atomic reservoir anchors the planet's long-term stability, maintaining our world from the inside out.